Okay, I just started the recording,
Okay.
and let's see here. Choose this here. All right. So anyway, how's the homework coming along? Any issues? Any hiccups? Technical issues? Statistics issues?
No, it went pretty smoothly.
Okay. Okay.
Yeah.
Very good.
It wasn't the easiest thing, but I managed. I tried.
Yeah. Okay. Well, yeah. Just let me know how it goes if there's any issues or hiccups along the way. It'll be a little bit of a change of pace if you haven't gotten to the chapter 1 skills check or chapter 1 skills review. That's a little bit different from the other stuff we've been doing. So let me know how that goes as well. So far on the modules section of Canvas, you can see how you can review what we did talk about on Monday and Tuesday, as well as Tuesday's lab time. And eventually I'll have what we're talking about now uploaded onto Canvas as well. But anyways, yeah, so if there's not any urgent questions, we're going to pick up where we left off yesterday, which was not here, but closer to here. I think, so we were talking about, let's see here. There it goes. Yeah, so we started talking about the difference between an observational study and an experiment. We talked about lurking variables. Replication and blinding is an important part of collecting samples. Double blinding is a thing. Randomization are things that are sort of underlying any kind of statistical analysis. I think we left off yesterday somewhere around here. I don't think we got a chance to start talking about sampling methods yet. So the remainder of section 1.3 is kind of exploring at least 5 common ways of producing samples, okay? Now this might come as a surprise because I think before I ever learned anything about statistics, I just thought you just go out and you just ask some people some questions and you got a sample. But there's actually a wide variety of ways in which you can take a sample. The most basic and most important one is a simple random sample. A simple random sample is just what it sounds like. You just grab a bunch of people, but every single person in the population has an equal chance of being chosen. Okay, now that last phrase is what makes it not be very simple. Okay, what do I mean by every person in the population has an equal chance of being chosen? I'll give you an example. Suppose I'm sampling people on public opinion, and I do this by making phone calls to people. I call 100 people and I ask them some sort of a survey question, right? Why is that not a simple random sample? In other words, why is it not the case that every single person has an equal chance of being chosen?
Possibly because people work at different times, so they might not be home at the same time.
Yeah. So if they're not home and I make a phone call, then they don't really have if they're consistently not home when I'm making phone calls, then they don't have an equal chance of being chosen. So that's a good example. Any other examples? Anyone else?
I'm assuming because it's random numbers.
Yeah.
So you leaving out a lot of other people.
Yeah. Like what I was thinking of personally was like some people might not even have a phone.
True.
If someone doesn't have a phone, then they don't even have a chance at all of being chosen. Also, too, if you're using like if you're choosing numbers at random, like let's say random from a phone book. Do people still use phone books?
I don't think so.
Yeah.
Well, a phone book is like one of those things that has, they typically only have landlines in them though, you know? So if I'm choosing phone numbers at random from a phone book, then I'm only calling people who actually have a landline. So a lot of people, like even myself, I don't even have a landline. I just use a cell phone. And I think a lot of other people are like that too. So people like that won't have a chance of being chosen. So to really be a simple random sample, the key phrase is that every possible sample of a particular size has the same chance of being chosen, meaning everybody has an equal chance of being chosen. Okay. The second of the 5 examples of random sampling is called systematic sampling. This is a different method of sampling. It says you select some starting point and select every, let's see here. Sorry, my screen's a little hard to work with. I have this. Okay, anyway, you know, I have to do it like this so I can see everything. Okay, there we go. So systematic sampling, that's where you take, for example, like there's a theoretical long list of cars, all lined up bumper to bumper. I can grab the third car as an element of my sample, and then from that point forward, just grab every third car from there on all the way to the end of the list. This would be a systematic sample. That make sense? Have any of you guys ever been in the LSC building at Pierce College?
No, I haven't.
Yes.
The library building?
LSC, that's also the library, the building where the library is found.
Is it like, I know the library is kind of like 2 stories. Is it underneath the library?
That's right.
Okay,
That's right.
yeah.
Yeah, I just mentioned it because I had a statistics class there last fall, and literally right outside the door of our classroom, there was a bulletin board for the geology department. And if we were on campus, I would tell you all to like go take a look at that bulletin board, because what they did, they're describing like some research that the geology department was doing, and they went to a certain site and they were measuring off 100 meters, and every 100 meters they took a sample of gravel, and they're looking at the composition of rocks. Does that make sense?
Yeah.
But every 100 meters, they'd grab like a handful or a cup of like gravel and then take it back to the lab and take their measurements. But this is also an example of systematic sampling. Anyway, that's the simplest systematic sampling. That's 2 out of 5. The third type of sampling is called convenience sampling. And so this is the use of data that's very easy to get. That makes sense? So convenience sampling, like the name implies, is the most common simply because it's easy, okay? But there could be a trade-off. What are the kinds of things that makes data hard to get?
Participation.
Yeah. An example, when you say participation, you know what comes to mind, because I watch way too much YouTube. You ever watch those YouTube videos where before you watch the video they want you to answer a question?
Yeah.
Yeah. And sometimes, just as my own personal protest, I'll just choose the first answer just because I want to get on with the video without even reading the question. So it's not it. So I would describe those YouTube surveys as convenience sampling.
Okay.
Because it's easy to get, but there's no guarantee that the people are going to participate, or if they do, they might just troll them kind of like I do. So yeah, so it's kind of hard to get good data, but sometimes you might have to compromise and go with convenience sampling. The last 2 examples are a little bit more complicated. The last 2 examples, a lot of people get them confused. Okay, so we'll try and dwell on this and let me know if you have any questions. It's stratified sampling and cluster sampling. So let's see what these 2 are all about. Stratified sampling is where you subdivide the population into at least 2 different subgroups. Sometimes we'll refer to those groups as strata. And the subjects within each subgroup share the same characteristics. So for example, an example of stratified sampling is if I take everybody in our class, I could break them up into two groups, the men and the women, right? So the men is a strata, the women is another strata. And then from each subgroup, I can select several men, and from the other group, I can select several women. And those 3 men and those 3 women together would be my sample. Does that make sense? So that way I can make sure, I would use stratified sampling if it's important that I make sure that there's an equal representation of men and women in my sample. So similarly, you might even see this like, you know, maybe based on race. If you have a sample that has a mixture of different races, I might consider each race a strata. And then if I want to make sure I have an equal representation of each race, then I'll make sure I grab at least several people from each individual race. Does that make sense?
Mm-hmm.
So let's compare now. We're going to take a look at cluster sampling and try to. And after we look at cluster sampling, I'm going to ask you what's similar and what's different. Okay. So cluster sampling, you can get, in this case, the example that you see illustrated is it's like basically all the people in like a city, and 3 of these blocks are highlighted in pink. So you divide the population area into sections or clusters. In this graphic, the clusters are blocks. And what I do is I randomly select some of those clusters and choose all, the key word is all, the members from those selected clusters. Does that make sense?
Uh-huh.
Mm-hmm.
So I randomly select all the members of those selected clusters. So in other words, so you can see how there's 3 blocks highlighted. Every single person that lives on each of those 3 blocks are going to be included in my sample. Anybody else that lives on any of the other blocks are not going to be included at all. So this might be more convenient, because if I have to have a team of people that are helping me out with this clustering, at least we don't have to walk as far. We just have to walk around the block one time. So what's the difference between cluster sampling and stratified sampling?
Using 2 different groups with
Mhm.
sampling, with stratified sampling, and then the other one is, I'm assuming, more than 2.
Yeah, could be. Let me go back to stratified sampling. In the graphic, you can see that it's broken up into 2 groups, or strata, but it didn't have to be 2 groups. We could have broken it up into 3 groups, or we could have broken it up into a dozen groups. In fact, I could even do stratified sampling in a city. What would, so I'm coming back to this graphic where you have a map of a city with a bunch of blocks. Suppose each of the blocks is not a cluster, but consider each block a strata. What would stratified sampling look like in a city?
You would divide the pink blocks into possibly the men that live in that block and the women that live in the block, and then choose only certain things from men and women from that specified block.
Ah, okay. Yeah, I think what you're describing is kind of like cluster sampling and stratified sampling combined.
Oh.
You could do that. You could do that. Yeah, it's kind of a hybrid of cluster sampling and stratified sampling. Yeah, let me clarify a little bit more. If I was to do stratified sampling, where the strata is each individual block. So this pink block is one strata, but this other block that's not highlighted is another strata. There's like a couple dozen strata or blocks shown in this picture.
Okay.
And so stratified sampling, just like here where I just grabbed some people from each strata, stratified sampling would be to take some people from each block.
Mm.
So the strata would be the blocks.
Exactly.
Okay.
And the key is I'm grabbing not, you see what, like with cluster sampling, see how I'm grabbing everybody from from each cluster?
Right.
With stratified sampling, I'm grabbing some people, not all people, only some people from each strata.
Okay.
Yeah.
Got it.
So yeah, so you'll be in the homework. There'll be more questions where you'll have to sort of, but those are the questions you're going to be asking yourself. Am I grabbing everybody in each cluster, or am I grabbing some people from each strata? And that's how you're going to decide whether it's cluster sampling or stratified sampling.
Got it.
Cool.
Makes sense now.
Yeah. Yeah, I'm sure you'll have more questions tomorrow, but I think you got it enough to kind of get started on the homework for sure. Okay, so I think this is the last two definitions for this section. It's talking about sampling errors. Okay. Now, errors are a bad thing. We generally try to avoid errors, but in statistics, there's certain errors that are unavoidable. Okay, let me rephrase that. There's always some errors that you can avoid. There's other errors that you cannot avoid in statistics. Okay. So what do I mean by that? No matter how well you plan and execute a sample collection process, there's likely to be some error in the results. Sampling error occurs when the sample has been selected with a random method, but there is a discrepancy between the sample result and the true population result. So, for example, I'm assuming that everybody have you ever messed around with rolling a die before?
Yes.
So, not to take anything for granted, I would assume that most of you have played with dice sometime in your life. That's one of those six-sided sort of objects. Looks something like this. And each side has these like pips or dots. So maybe there's like 3 little pips along here. So if this side comes up on top, then that means you rolled a 3. And then, but if the side with 1 dot comes up on top, that means you rolled a 1. And since there's 6 sides to the die, that means you can get any of the numbers 1 through 6. And as long as each of the faces is square and everything is perfectly balanced, then each number has an equal chance of coming up. So bearing that in mind, if you roll a die 30 times, and each time you record what number comes up, how many of each number would you expect?
1 out of 30, because each time that you roll, you basically have the same chance of rolling the same number.
Yeah, exactly. So since you have the same chance of rolling each number, how many 1s would you expect to get? And after you answer that question, my next question is, how many 2s would you expect to get? And how many 3s would you expect to get?
That kind of method is almost impossible to predict.
Yeah, you're right. It's hard to predict, but you can make an educated guess. So I'll put it this way. Let me put it this way. If I have an equal chance, if each number has an equal chance of coming up, I'm going to be getting one of these 6 numbers, right? 1 through 6.
Mhm.
If each number has an equal chance of coming up, then I would expect how many ones? Well, it wouldn't surprise me if it wasn't exactly what I would predict, but I would expect it to, I can come up with a pretty good guess. With 30 rolls, I would expect the same number of ones as twos. Now, chances are it won't be exactly the same, but I would expect it to be pretty close. I would expect to say it have the same number of threes as well. I would expect each of these 6 numbers to come up about the same amount of times because there's an equal chance of each of those numbers coming up. And if you take 30 divided by 6, you get 5. You still with me?
Mhm. Yeah.
So I would expect five ones. And I would expect, because there's an equal probability of getting a 2 as there is of getting a 1, I would expect 5 2s as well. In fact, I would expect about 5 of each of those numbers. Does that make sense?
Yeah.
Here,
Yeah.
give me a second here. I actually have a die. Some dice over here. So here's an example of a die. Okay, I'm not sure. Let's see. I think what I can do, I get a 3 here. I get a 5. I get a 4. Okay, well, I'm not gonna roll this 30 times, but if I did, I would expect to get 5 of each number. Now, chances are some of these, I would be surprised actually if they were all exactly equal to 5 in reality. But that's what I'm referring to by sampling error. Okay, although I expect the same number for each of those 5, the same frequency for each of those 6 numbers, I wouldn't be surprised if the sample result was different from the true population result. Okay, that's an example of sampling error.
I have a question, Professor.
Yeah.
So is this is a sampling error, possibly go along with like human error, or, because like, okay, you might be rolling it with like different force each time, like that also creates like a different.
Yeah, good question. Yeah, human error is a thing too, but it is different from sampling error.
Okay.
Like human error is something that's an example of an error that can be avoided.
Okay.
Okay, so if we're doing an experiment, in fact, one of the unfortunate things about doing this particular class online is like last quarter I had this class and we actually were rolling dice during the lab time, and I could go around and I could see human error taking place right in front of my eyes. So for example, I would see people sort of rolling their dice and they're just kind of going like this. And if you're too lazy, see if I'm just dropping it like that. Can you see it? What I'm doing there?
Yeah.
This is okay. Nobody was actually doing this. This is like way too lazy. But it's very rarely changes. You know what I mean?
Yeah.
You really want to kind of like roll it like this, and then drop it. Roll it like this, and then drop it. So even the technique with which I roll the dice can introduce an element of human error.
But it's not the same thing as a sampling error.
Exactly. This is
Okay.
not the same thing as sampling error. If I do this like with good technique, it wouldn't surprise me if I didn't get all 5s,
Mm-hmm.
right? So there is a distinction there. Let's see here. Coming back to here. And that's what I'm referring to when I talk about sampling error. This is the type of error that cannot be fixed, okay? And that's why statistics is a thing, is because even with the sampling error, surprisingly, we can still derive some meaningful information from the problem. And I think this is the last slide here. Oh, there it is. Just you were already ahead of me. Human error includes such factors as data recording errors, computing errors, questions with biased wording, false data provided by respondents, forming biased conclusions, or applying statistical methods that are not appropriate for the circumstances. That actually reminds me, I think, I wasn't planning on this, but I think I can pull it up real quick. So last quarter we did some, I had students collecting data, okay? We can't do the same lab that I did last quarter, but I can show you some of the data that we came up with. Here it is. Oh, I probably shouldn't be showing you people's names, but here's some of the questions that I asked last quarter. Is let me look at this one here. There is some funny ones. Oh yeah, so we had some kitchen scales in class, and I had everybody weigh their cell phone in ounces. Does that make sense?
Yeah.
Mhm.
So you can get out your cell phone, you can weigh your cell phone, and you can see as you go down the list, somebody had a cell phone that weighed 6.6 ounces. Someone else had a cell phone that weighed 6.84 ounces, 9.45, 4.9. But somebody apparently had a cell phone that weighed 0.04 ounces. Now, I suspect that was human error. I don't know if you know how heavy 0.04 ounces is. That's probably about the weight of a piece of paper.
Right.
You know what I mean?
Mm-hmm.
So I
Maybe
think
that was their cell phone.
yeah, that's true. Yeah, maybe their cell phone is they make a paper airplane and they throw it to the person.
Yeah.
Or here's an interesting one. I suspect there's some human error right here too. Or else somebody had a brick for a cell phone. 63.1 ounces? You know, there's 16 ounces to a pound, right? So that's like, how many pounds? That's like a 5-pound cell phone. You're gonna break your back carrying that around in your pocket. Oh, that's even worse.
Oh, wow.
868. So now if I had to guess, I think they just forgot to put in the decimal point. You know what I mean?
Yeah.
They
Yeah.
probably meant 8.68 ounces, right? But these are examples of human error, right?
Okay.
And last but not least, in addition to that, we have non-random sampling errors. The result of using a sampling method that is not random, such as using a convenience sample. Remember how we mentioned convenience sampling?
Mm-hmm.
And here's a word that you're going to see coming up in the homework: voluntary response sample. Okay, so we'll go back to that YouTube video survey that I was talking about earlier. That's kind of a voluntary response sample. You know, these are voluntary response samples are notoriously bad, simply because it's biased towards the people who volunteer to respond. Does that make sense?
Yeah.
Mm-hmm.
The people who, you know, for example, if I'm doing a voluntary response sample for what am I thinking of? I'm thinking of an example like, how do you feel? If I do like an online survey of like, how do you feel about technology? Well, the people who are going to volunteer to participate are probably people who feel comfortable with technology. You see what I mean? The people who don't feel comfortable with technology probably aren't going to participate because they wouldn't even be on the internet or something like that. Anyway, so I guess in short,
Talk now. I am on a video.
in short, voluntary response sample is bad. Okay.
Now. Very disappointed.
So anyway, so that concludes this section 1.3, and hence concludes chapter 1. So as you can see, chapter 1 between 1.2 and 1.3, it's really a lot of definitions. Okay.
Mhm.
So I'm going to change gears here. I don't think we're going to have time to finish today, but I do want to get started on chapter 2. And the homework that you'll be working on over the weekend will include 2-2.1, and eventually, starting on, I guess, sometime next week, we might even take a peek at it on Friday. We'll eventually start getting to 2.2-2 and 2-4 next week. But for now, just want to kind of get an idea of what chapter 2 is all about. I guess based on the title, it's exploring data with tables and graphs. So chapter 1 was a lot of definitions. Chapter 2 has a lot of tables and graphs. So we're going to jump into that. The key concept is when working with large data sets, a frequency distribution or table is often helpful in organizing and summarizing data. So the whole point of chapter 2 is organizing and summarizing data. A frequency distribution, have you ever heard the word frequency before?
Mhm.
I think that word frequency throws people off a lot of the times. So it helps if you've heard that word before. Frequency is just a count. We're going to count how many, we're just counting numbers, okay? But it shows what we do is we break up the data into several classes, and then we count how much data is in each class. So I'll show you what I mean in a second. So McDonald's lunch service times. So everybody knows what McDonald's is, I assume. It's a fast food restaurant, popular with a popular drive-through service feature. Drive-through service times in seconds for McDonald's during lunchtime. So how long is the typical wait at McDonald's? Now, as you look at this table, we see a whole bunch of 3-digit numbers, 107 in the top left, 139, 197. Each of those numbers you should interpret as being time in seconds. That means that somebody drove through a McDonald's drive-through at lunchtime, and apparently someone was lurking in the bushes with a stopwatch. And it took about, from the time they placed their order to when the order was ready, it took 107 seconds, so almost 2 minutes. Somebody else took 139 seconds, or just over 2 minutes, for their order to be filled, and someone else 197, and so on and so forth. I think there's 50 numbers in this list. So at a glance, what do you think? What's the typical wait time at McDonald's?
You have to get the mean by adding all of them up and then dividing by the number of
Total of numbers you have.
That's
taken
right.
times.
That's right. That's right. And actually, that's a good answer. In fact, actually, when we get into chapter 3, that's when we'll be doing that. That's when we'll be doing that. So you're way ahead of me, which is good. Yeah. So we're going to be repeating this discussion when we get to chapter 3. What you're talking about is you're finding the average, or the arithmetic mean. You add up all 50 numbers and divide by 50. That would be the average wait time. In chapter 2, we're not going to be calculating the mean, okay? We're going to use a frequency table to see what a typical wait time is, okay? So that might be, this might be a little, a new idea to you. But even without the table, I just at a glance, I'm not really looking at all the details very carefully, but I can see that they're mostly 3-digit numbers. They're mostly in the hundreds. So at a glance, I'd say between 1 and 200 seconds, 2 or 3 minutes.
2 to 3 minutes, yeah.
Yeah. And what you see now down below is an example of a frequency table. Okay. Now, what you see in the table is a summary of the data above the table. That make sense?
Mm-hmm.
In the first column, it's the time in seconds. And in the first row of the first column, you see how it says 75 to 124 seconds.
Mm-hmm.
That's an example of a class. It's a range of times. And if you go through that table and count how many of those drive-through service times was between 75 and 124 seconds, you're going to count 11 numbers. So like that would include this 90 right here. That would include 113 over here, the 91 over there. That makes sense?
Yes.
And similarly, if that second class is from 125, see how it picks up right where the other one left off? From 125 to 174. If you count how many numbers are in that range, there's about 24 drive-through service times in that time as well. Okay, so about this time last year, I was having a conversation with my nephew. At the time, he was about 12 years old, okay? And we were looking at not this example, but something kind of like this. And we had an interesting conversation because I asked him, you know, what do you think is better? Is it better to have all the data like this or to have this table summary right here? And what he said to me, I thought was kind of interesting. He said, well, isn't it better to have all the data? Because sure, there's 11 numbers in that range, but I don't know where they are. Does that make sense?
Yes.
And I could understand his logic. I can't argue with that. You know, it's true. To create this table, this frequency table, I've kind of lost some information, right?
Mm-hmm.
But I tried to show him that, like, in a way though, I've somehow gained some information, in the sense that if I don't see, if I'm only looking at the numbers, it's really, all I can really say is they're all somewhere between 100 and 200 seconds, right? But by breaking up into classes and counting, I have a much more refined idea of the distribution of times. I can now see that most of them are actually specifically in the range of 125 to 174. And although it does from time to time get as high as 200, that's very rare. And in fact, it was never less than 75 seconds. So it's debatable, but I think if I want to be able to just look at the data and just immediately have a sense of how the numbers are distributed, I think the frequency table is preferable. Okay, so, oops, wrong button. What am I trying to do here? There it is. Okay, so a couple more definitions. In each of my classes, I have what's called the lower class limit. It's the smallest number that belongs to each class. The upper class limit is the largest number that can belong to each of the different classes. So if we come back to my frequency table, how many lower class limits are there? Well, the first class has a lower class limit of
75.
Yeah, that's right. So, and similarly, the second class has the lower class limit of 125. The last class has a lower class limit of 275. So how many lower class limits are there? Looks like 1, 2, 3, 4, 5 lower class limits. And then I could also ask, what are the upper class limits? So you're going to come across some homework problems where it's literally going to say, like, what are all the lower class limits? And for each class, we can talk about a class midpoint. Now, these are the values in the middle of the classes. Each class midpoint can be found by adding the lower class limit to the upper class limit and dividing the sum by 2. So what is the first class midpoint? Actually, that's kind of hard. You might need a calculator to do that, but more importantly, how would you calculate the first class midpoint? So it says here, each class midpoint can be found by adding the lower class limit. So for the first class, the lower class limit is 75. And for the first class, the upper class limit is 124. If you add those two together and divide by 2, you're going to get the first class midpoint. I'll just pull up my calculator here. So yeah, let's see here. Where was I? This one right here. All right. Where did it go? There it is.
You get 99.5.
Yeah, you got it. Yeah, I was just trying to demonstrate it here. I'm just having trouble making the screen so that I can see everything that's going on. But yeah, what do we got here? We got, so the lower class limit is 75, the upper class limit is 124, and the average, or the middle of that class, is 99.5. Is that what you said?
Yes. Well, I said 99 point. I don't know, 5. Yeah, I said it.
Okay, good. Okay, yeah. So that's the exact middle of that first class. And so similarly, you could take 125, right, plus 174 and divide that by 2. That would be the second class midpoint. Now, the last one is I think is the trickiest one, the class width. The class width is a little bit counterintuitive, so you want to pay attention to this one. How am I doing on time anyway? Class width is the difference between 2 consecutive lower class limits. Okay? Now, if I didn't know any better, I would want to take the difference between the upper class limit and the lower class limit, but that's not what it says. It's the difference between 2 consecutive lower class limits. So what is the class width?
Of the would you just find the average of all of the lower class width? The lower class limits?
Close. But
Would you
not exactly
subtract?
that. Say again?
Would you subtract a class limit from another class limit?
Yeah. So I'm looking at the lower class limit of each class, right? So for example, if you look at the first class and the second class, the first lower class limit is 75, the next lower class limit is 125, and the difference is 50. And notice if I look at the second and third classes, 175 minus 125 is also 50. Now, in fact, one thing that's kind of important is that whenever you're doing this, let's see here. All right. It's important that all the classes must have the same class width. All the classes must have the same class width. So you can see how in each of these cases, the class width is 50. And so, in fact, if you notice, if you add 50 to 175, you get 225. If you add 50 to 225, you get 275. So in this case, in this example, the class width is the same for all of them, and the class width is 50 for all of them. So in this next example, okay, now on this slide, this will make more sense as I explain it, but basically these are step-by-step instructions for how to construct a frequency distribution. How to construct a frequency distribution. And so I'm gonna, all of these, like these 6 sort of like step-by-step instructions are gonna be described in the next couple of slides, so I'll just jump straight to it. What I want to do here is we're returning to the same original drive-through service times for McDonald's, and step by step in my instructions are to select the number of classes. Usually somewhere between 5 and 10 classes is a good idea. Okay. Now, we already found a frequency distribution and it had 5 classes. We're going to use the same data, but we're going to come up with a distribution with 6 classes instead of 5 classes. And so what we're going to do is we're going to select the number of classes, and we're going to have 6 classes. We're going to calculate the class width by taking, let's see here. Ugh, why is this thing? Okay, there it goes. So you can see how the largest number was 308. The smallest number was 83. So that means I have the drive-through service times have a range of 225 seconds. If you compare the largest drive-through service time and the smallest drive-through service time. But if I want to divide that up into 6 classes, I get 37.5. And it says to calculate the class width, we want to round up to a convenient number. In my opinion, so what do I mean by a convenient number? I mean something that's like a round number. So instead of 37, I think 40 is more convenient.
40.
Does that make sense? Mostly because it ends in a 0.
Yeah.
So instead of having a class width of 50 like we saw before, we're going to construct a frequency table. We might not have time to finish it today, but but we're going to construct a frequency table that has a class width of 40 instead of 50. And step 3 in my step-by-step instructions was to choose the value for the first lower class limit. Okay, I think in the previously we used 75 as our first lower class limit. Is that right?
Mm-hmm.
Well, this time it's usually going to be a convenient number. Again, what do I mean by convenient? A multiple of 10 or maybe a multiple of 5. That's less than the minimum. So the minimum is 83. I need some number that's smaller than 83. I think
Like 80?
yeah, that's exactly what I was thinking. Like 80 would make a lot of sense.
Okay.
So if I put in an 80 for my first lower class limit, if the class width is 40, then that automatically determines all the other class limits. You see where the 120 came from?
Yes.
Yeah. If the class width is 40, then the difference between the two lower class limits should be 40. So 80 plus 40 is 120. Likewise, 120 plus 40 is 160. 160 plus 40 is 200. 200 plus 40 is 240. 240 plus 40 is 280. Next, we want to determine the upper class limits. That's step 5. We're going to do that by taking each individual data value and put it, oh yeah. Okay, step 5 is, so what should the upper class limits be? Remember how the upper class limit for the first class should end? So the first class should end right where the second class begins. Does that make sense?
So it
Mhm.
would be 119.
That's right. That's right. And let's see here. There it is. So the first class is going to go from 80 to 119. The second class will go from 120 to 159 because 159 is one less than 160. See what I mean? So you can really just take the lower class limit of the next class and subtract 1. Now the tricky thing is when you get to that lower class, the last class, the one that begins at 280, where did the 319 come from?
That's what I'm confused about.
Yeah. Well, I guess if I had a 7th class, I would have added 40 to 280,
Okay.
which would be 320, and 320 minus 1 is 319. That's one way to figure it out. Another way to figure out, and I can only do this because all the classes have the same class width. You could also think of it, notice that the difference between each of the consecutive upper class limits is also 40. So 279 plus 40 is 319.
Mhm.
So that's the only tricky part, I think. But once you have determined the classes, the remaining steps is to just simply count how many numbers are in each class. So I highlighted some of them just to make the counting go a little quicker. But how many numbers are in the range of 80 to 119? Let's see here. That looks like, I think those are the ones that I did in blue.
The dark blue, right?
The dark blue, yeah. You see that? So let's see here. 1, 2, 3, 4, 5, 6,
10.
7, 8, 9, 10. Yeah, 10. I see 10 as well. And then the number of numbers that's between 120 and 159, I think I highlighted those in aqua, kind of an aqua blue, right? Looks like there's more of them.
Yeah. The lighter blue.
Yeah, that's right. And I think you end up with those numbers. So it's kind of a similar distribution to what we saw when we had 5 classes. See how most of them are kind of right in that range of 120 to 159. But then then there's some that are smaller, some that are bigger, that sort of thing. Okay. So anyway, I think we're probably at a good stopping point. There's still a little bit more to talk about from this section, but tomorrow we'll pick up where we left off. But you should. I think we've gone over enough that you should be able to finish chapter 1, and maybe even if you have time to start, doing what you can from section 2-1. Okay.
Yeah.
So the